right, hey everyone. Welcome to the Ice Giant Systems seminar series. You're probably usually expecting Mallory. She's not here today, so I'll be filling in a little while she's out, but I'm sure next time around we'll have her back in. But today we've got Dr. Jessica Weber. So I'll read a little bio, then if you want to share your slides, go for it. So Dr. Jessica Weber is a Jet Propulsion Laboratory research scientist in the Origins and Habitability Lab. She earned her PhD in chemistry from MIT in 2019 with Dr. Tim Jameson and a BS in chemistry from University of Chicago in 2014. Her graduate school research focused on organometallic catalysis. I practiced that so many times and I still messed it up. Organometallic catalysis and pharmaceutical synthesis. At JPL, Jessica focuses on applying synthetic chemistry techniques to address questions about the origins of life and habitability of the early Earth and other worlds. She experimentally explores mineral-organic interactions and reactivity related to prebiotic chemistry on ocean and terrestrial worlds. So yeah, Jessica, feel free to take it away. We'll have your talk followed by a Q&A discussion, community news at the very end, but feel free to take your time and answer questions either through the chat or if people want to unmute, anything like that sounds good. So I'll turn my camera off just so that I'm not like a distraction, so that the focus is on you. But yeah, thanks so much for being here, and the floor is yours.
Awesome. Well, thank you so much for having me, and thank you so much for the invitation. And I'll pass that along to Mallory as well. I hope she feels better soon. So I think maybe I have a different background than a lot of the speakers that come through, but hopefully, I can share with you today a little bit about how I think astrobiology can be applied to the Uranian moon system. And I'd be remiss if I didn't mention my co-author in this, which is Aaron Leonard, who I see is also online. And we recently, a lot of what I'll be talking about today has been summarized in a perspective piece that was recently accepted to Astrobiology. And so with any luck, it'll be online today, but I'm sure all of you know how the journals work. So hopefully it'll be online soon. So with this crowd, I don't think I have to lecture very much about the Uranus orbiter and probe mission concept, but I'll keep it very simple and just say that this was the highest priority flagship in the 2023 to 2032 Planetary Science and Astrobiology Decadal Survey, right after Mars sample return. And there's a large variety of questions and topics that could be addressed by such a mission. Of course, looking at Uranus and its magnetosphere, looking at the rings, and what I'll be focusing on today is looking at the moons. Also in the Planetary Science Decadal Survey was 12 priority science questions, and very interestingly, section C, as you'll see here, is really focused on life and habitability. So question 9 is about what we can learn from terrestrial life. Earth is our one example of a completely biotic world. Question 2 is on dynamic habitability throughout the solar system. And question 10. And then question 11 is searching for life elsewhere. And so this is very exciting, and astrobiology was actually included in the title of the decadal survey this time. So, clearly this is something very relevant to think about and very supported by the decadal. And so looking at the origin of life and astrobiology on Earth is very relevant to the decadal survey. And as Jody mentioned, I am a chemist, and this is, a really fun connection for me because life is made up of carbon. So organic chemistry is very relevant to origin of life and astrobiology research. Many of these origin of life and astrobiology questions are very relevant to the synthesis, distribution, reaction of organic molecules. So looking at this, it could be the, availability and synthesis of biomolecules or molecules used by biology, ratios of organic products under different conditions, comparing abiotic and biotic reactivity. And in my brand of research, in my lab group, we seek to answer these questions through laboratory experimental procedures, actually testing what this is in lab. But in order to do this, we need to look at some geologic conditions that we are going to test with. As in our planetary system, we are surrounded by geologic environments. And so in order to do this, we need to find reactive sites to actually mediate organic chemistry. Iron minerals are a great example for this. Minerals and metals are abundant on Earth and other worlds. We know iron makes a lot of appearances in our solar system. And importantly, many mineral-rich locations on Earth are places that have been hypothesized to possibly be sites for origin of life type chemistry. And we know based on work done in my research group and others that iron and other minerals are capable of mediating organic chemistry. And so here's some science questions that we seek to answer. Can these minerals mediate reactions relevant to life? What kind of minerals are needed for this reactivity? And looking at the presence or absence of these minerals or organics, what can this tell us about habitability of these different environments? And so life detection is an important part of astrobiology. However, it is a huge subcomponent of what astrobiology actually is. This is a really wide field looking at a lot of questions, but in order to understand life detection, we need to understand what not life looks like. And so if you go out and scoop up some dirt on Earth, most of what you're going to find, even the small organic molecules, are biotic. However, on an abiotic world, or a world that's kind of on the pathway prebiotic, to origin of life or something like that, you may be able to find much more complicated chemistry that's made abiotically. And constraining this is important for a variety of reasons, including contextualizing data from missions, actually making sense of these missions, knowing what to expect when we go to other worlds, evaluating biosignatures and looking for life. Really important to know what the limits to not life are to find life. And then understanding just generally what abiotic chemistry is capable of for habitability. We know we need organic molecules to have life as we know it. And so understanding its abundances and where these show up is going to be really important for that. So like I said, I'm an experimentalist. And how do we actually test this on a very biotic world where life covers everything? So we use a laboratory setting at JPL in the Origins and Habitability Lab. And a lot of this is, to the best of our ability, recreating different planetary environments in a very controlled setting. So we have anaerobic conditions. We know the early Earth was anoxic. So we use a glove box, of course, given your preference and setup. You could certainly imagine another anaerobic or another gas mix that you would like to use. We use iron minerals or other planetary relevant minerals. And then from this, we take specific conditions, so pH, temperature, pressure, so on and so forth, to test our reactions. And while a lot of this is very specific to Earth, especially for origin of life type chemistry, again, this is important because Earth is our one example where we're very confident that it's a biotic world. Life has been very successful here. We know there was origin of life type chemistry to start kick everything off. And applying what we know about Earth to other worlds is going to be really important for answering questions about origin of life. But aside from that, the reactions are just run under a set of conditions. So if we're running, say, an aqueous experiment at a certain pH, a certain temperature with certain salt concentrations, there's no reason this isn't also applicable to environments on other worlds, including Mars, ocean worlds, the Uranian moons. We can really apply these broadly because, we can spin it, of course, as an early Earth reaction and a Enceladus reaction, but these are just a series of conditions. And if the conditions apply elsewhere or can teach us something about worlds elsewhere, then they're relevant. And of course, this is, as I mentioned earlier, important for searching for life and important for mission concepts, as it, informs us of what organics could be believable on these worlds. And so I just wanted to shout out my lab group. I co-lead the Origins and Habitability Lab with Lori Barge, and we have a bustling lab group. Like I said, we're experimentalists, so I have a nice little video of a chemical garden growing here. We have undergraduate, master's level, and PhD interns that work either throughout the summer or year round, doing a lot of this work. And it's a really fun lab to work in. So if you have any questions, please reach out. We'd love to talk to you about our work. Our work focuses on 4 main topics. And you'll see that these fall very well into the introduction that I just gave. Planetary geochemistry and habitability, hydrothermal vents, astrobiology and life detection, and then the emergence of life. And so before we get into the Uranus part of this talk, I have a few caveats I'd like to spell out. I completely understand that there is a mission concept for UOP. I understand that there was a proposed payload for this. And so I am certainly not advocating we throw the baby out with the bathwater and completely scrap the mission to make it all about astrobiology. I don't think astrobiology needs to be a key mission driver for this. this is not this is not what this talk is going to be about. And as a chemist, I really would love a chemical inventory of all of these moons. However, I recognize, again, as astrobiology is not a main driver, there are other science questions. Many of the very, very detailed measurements that I might love to have may be out of the scope of this mission or range of detection for what we want to do. And then astrobiology as a field is very broad. This includes biology, geology, chemistry. And so it's not just life detection. So I am not advocating that we do a life detection mission for UOP by any stretch of the imagination. I think that is well out of scope. And then what I'm talking about today is one brand of astrobiology. So I'm an experimentalist. I am a chemist, and these are the things that I think are important based on the Cato survey and my research. But certainly, I see people in the audience who I would also consider to be, at least astrobiology adjacent if they don't identify as astrobiologists themselves. And they have very different brands of research. And so I hope to show how some of these can connect. But again, this is one perspective on this. And so I'm going to briefly walk us through the Uranian moon system, which includes the smallest Miranda, and then Ariel and Umbriel, Titania and Oberon. And maybe to spoil the punchline, I'm going to start with a few tables. So the first thing I'm going to look at here is this is a really nice table done by Julie, where it kind of contextualizes the solar system moons based on their radius and density. And so you can see, Miranda kind of falls into one box, maybe similar to Enceladus. And then the other four are maybe closer to, Ceres or other moons, kind of all falling into the small, medium, icy satellites arena. And then from Aaron and I's recently accepted paper, this is kind of summarizing what we know about these moons based on their, data from Voyager 2, current state of knowledge. And we split this into 5 categories based on habitability recommendations for the decadal survey and previously published literature. So the first is size, which, plays into the potential to sustain a subsurface ocean. And I should also say the orangey color means that, based on current data, it likely does not fit the broad habitability criteria. The gold or orange colors mean that we just really don't have enough data to know it's possible, but we really need more information. And then the green means that this likely could fall into this box of possible habitability. So for size, like I had said, Miranda is the smallest, followed by Ariel and Umbriel, and then the larger two fit into a much happier size range. Luckily for us, we have detected water, liquid or ice on all of these bodies. And then for geologic history, looking at evidence for surface features, Miranda and Ariel at least seem active in recent history. Umbriel is a little quieter. And then for the final two, we don't really have enough data to make a conclusion on this. And you can see the Voyager 2 image resolution in the brackets. And so this did vary quite a bit across these bodies. Luckily and very comfortingly for me, the composition of these moons has been shown to be interesting. And so we see CO2 as well as nitrogen-based compounds and dark material on a number of these moons. And then as far as energy, there's a lot of unanswered questions for this. So the boxes are gold across the board. And just briefly going through the moons, mostly as an excuse to show you some nice images. Here, like I said, Miranda is believed to be too small to currently maintain an ocean. However, there is relatively recent activity, and it's likely endogenic. Ariel also has some very interesting features on its surface. Umbriel is the darkest of the main satellites, and its surface features are debated, but there is some nice bright material that we found. Titania does have some surface features throughout it and is believed to have some activity. And Oberon here has some bright material, dark units, and then a few features on its surface. And so overall, over this brief moon tour, there's significant unknowns about energy sources and surface activity. The composition does look promising, but and there's been really great work even recently that I'll highlight in a little bit to nail some of this down. But we really don't know. We don't have a full organic, or for that matter, inorganic inventory of what these moons are. And there's a lot of material that hasn't been identified on the surface. And our knowledge is limited by data quantity. Anyone who works on a spaceflight mission knows that you are limited in flybys, and you are limited in what you actually get. And certainly your very high resolution, lab instruments might give clearer spectra than what we're getting from spacecrafts. And so for this, I wanted to just highlight a few connections I see from these moons to astrobiology. So these would provide an additional data set on putative ocean worlds. As we saw from the chart that I showed earlier, these moons fit into a larger picture of moons and small bodies that we found in our solar system, and understanding how and where oceans exist could be a critical data point in comparison to what we know about other ocean worlds. And these could fit into a broader picture constraining what we know about worlds like Enceladus, Europa, Ceres. And then even if it's not habitable, and not that I'm saying in this mission we will be able to definitively answer habitable yes or no, we really don't have a confirmed example of a completely abiotic ocean. Like on Earth, as I said, life's taken over quite a bit. And so anything we sample, it has been affected by life. And when we look at the range of what we see in the solar system, I think it would be interesting to have this null example, better characterized. And so even if these worlds aren't, the most exciting for life detection, we think there's bugs there. This is a really important, perspective that we could have for the solar system. And then better constraining and understanding ocean presence, characteristics, and organic and inorganic cycling is beneficial to astrobiology as well. This again kind of fits into the abiotic ocean. All of our cycling on Earth is really affected by life as we know it. And having examples and better understanding how these materials move in other worlds, gives us a broader picture of what chemistry and astrobiology is capable of. And so this is a extremely non-exhaustive list, but Aaron and I did nail down some interesting science topics for astrobiology and some potential measurements. Again, these are just examples designed to kind of spark discussion, non-exhaustive. So I'm very sorry if I left out your favorite technique, but we would love to hear about it. So the science topics are current activity, which we think could be probed by camera and magnetometry measurements. Then ocean presence and conditions, including temperature information. And for this, we could access this through gravity or libration measurements, magnetometry, and radiometry. Then we could look at ionic composition, looking at what the inorganics are doing. There's spectroscopy that can give us information on this, as well as something that's in situ, where you're actually detecting samples directly with something like mass spec. Ice shell thickness and properties are also important to understanding an ocean. For this, something like gravity or radar would be helpful. And then, of course, for organic chemistry, you could use spectroscopy as well as mass spec as well. And all of these references that we have are from missions like Cassini and Dawn, which have done this in spaceflight. So we really tried to constrain ourselves for this to techniques that have been used in flight before. And then I just wanted to give a brief example here of Cassini. which was a flagship mission to explore Saturn and its moons. And Cassini discovered and sampled the plume on Enceladus with some of the mass spec instruments, like I was talking about. And there's really two things I want to highlight, kind of for discussion with Cassini. Is the first is Cassini had no idea that the plume was there before, right? This was detected in space flight, and was kind of, a fun surprise. And there are still publications coming out on the two mass spec instruments, which is INMS and CDA from Cassini. And so even many moons after the mission has ended, we are still, the science community is still, profiting basically from this data. And now we have much higher resolution mass spec instruments that really could, provide a lot of new information. And so, just not to belabor the point of Enceladus, but there was a lot of information we gained from flying through the plume, not only looking at the organics and inorganics and kind of constraining what's possible in the ocean through that, but there was some information that hydrothermal activity could be on the seafloor from the plume. So I think that, just to say that these flagship missions, provide a lot of data that I'm sure goes into many papers and theses, and really expands how we know about these worlds. And so, what can we do to prepare? We do have a while before UOP flies. And I think there are a number of research types that we could use to better prepare ourselves for the mission. Laid out here, it includes observations, modeled or theoretical studies, and experimental tests. So we're ending on my favorite, what I'm the expert in, but I will touch on the other two, mostly in how they relate to what I want to do. But I would be really curious to hear from people who are primarily in these fields, to how kind of the experimental tests and other things can feed back in. And so again, all of these can fit into, whether or not it's specifically, written as astrobiology research, all of these can fit into better constraining the dynamic habitability and whether or not this is a realistic place to look for life. And so the JWST observations have garnered some very beautiful images. And I think this is, of course, great press for Uranus and the solar system, based on these observations. But we have learned more from recent observations that can help us prepare for future missions. And recently, recent work by Cartwright et al. Showed that there's CO2 ice, CO ice and CO2 deposits on Ariel. And so, this, I've included one figure from the paper, but, you can see there's a variety of, compounds even within this that could be on the surface, including, more oxidized or more reduced carbon species, carbon nitrogen type materials. And so this is something that I can see, really playing into experimental research. This gives us at least a starting point to stand on with carbonates, which are available, and these different CO and CX materials. And so with these observations, we can better prepare ourselves not only for the experiments and models, but to really get us knowledgeable about what to expect on these moons. And then just touching briefly on some modeled work, recent work by Julie and co-authors, worked to constrain if there could be subsurface oceans on these worlds, based on a variety of factors. And it found, as I kind of hinted at earlier, that while Miranda likely cannot sustain an ocean over geologic time, the others may have current day shallow oceans. And from this work, I wanted to also include this summary of possible heat sources. As I said, based on what Aaron and I had collected, there's still a lot of unknowns on the heat sources. So I really liked that this laid down, both the origin and then the type of heat, and then, ranked it from major source to unlikely. And even in the potential, let's call it some cases, it laid out, what would influence that. And so I thought that was, really, really helpful for a broader understanding of, what could be around. And then, again, for the experiments, which is my expertise, as I implied earlier, all experiments are ran under a specific set of conditions. You're looking at temperature, pressure, concentration of your organics or inorganics, pH, these levers that you pull for the experiments. And, while you're targeting specific bodies, there's no reason these cannot be applied to other worlds. And then, based on previous experiments that we've tested with prebiotic materials, and then, these new modeled studies, these new observations, we can then design better experiments for the target body. And so I'll just run through a couple very quick examples. All of them fall into the theme of having alpha keto acids as a reagent. So alpha keto acids are metabolically relevant reactive molecules. We know, based on a lot of work, that these molecules can access alpha hydroxy acids, which are important prebiotic precursor molecules via reduction. And then via reductive amination, we can make amino acids, which we know and love are the building blocks of peptides and proteins. So, from this, we can then, take these and test them with a reaction network. And so based on work out of the lab group, we know that these are reactive with iron oxyhydroxide minerals that we can make in-house and tune with oxidation state. But one thing that we noticed is based on the set of conditions, you get different products. So you can either favor the reduction or the reductive amination. And this is different for different alpha keto acids. And so there's not some one size fits all where we can say in all cases at high pH, high oxidation, you make X more than others. And so here is just a table that I really like, or that lays out based on reduced or oxidized iron and pH 7 or pH 10, what material is made for. So if you look at very oxidized conditions at pH 7 for the glycine family, let's call it, you're primarily making glycolate. But the same is not true for the alanine family. And if you look at a different pH, then you've really changed the levers and you're making a lot more glycine at this point. And so the geologic conditions and the conditions you pick heavily influence reactivity. And so if we have any knowledge about what could possibly be, minerals that are available, materials that are available, general conditions, this is something we can test. And of course, you can pick which lever to pull. If you want to say explore carbonates experimentally, then there are other things that you can vary and kind of leave as unknowns. And then from this, we don't just have to do necessarily aqueous chemistry. We can take our materials, such as our alpha keto acids, and irradiate with and without minerals to see if we get reactivity. And so this is a recent study. It was based under we called it series conditions, but we were really just irradiating these materials with a UV lamp and seeing what came off when the lamp was on and what changed when the lamp was off. And so, as you suspect, when we were radiating, we saw more reactivity. But these are just two very general setups that we can test, and they can be quite general to different planetary conditions. And so, just some ongoing experimental considerations. All of these forms of research benefit each other, and moving into recommendations is, I really hope that you will consider astrobiology as investigations as a requirement on instruments. Again, this doesn't have to be the focus, but there's a lot of information that we can gain, from a study like this, a mission concept like this. And this is, something that we should be maybe part of the conversation. There should be more discussion on cross-disciplinary science. based on kind of what I've talked about with the observations and the modeled work and the experiments, these can all really flow together quite nicely. And I want to consider integrating ongoing astrobiology research, whether it's experimental, geochemical, geophysical, to help narrow down these measurements. And if I could pick one instrument that I would like to add to the mission, I think having a dust detector mass spec would provide, critical organic measurements for this system. We're missing a lot of data on the organics in this arena, and this is a really great technique to get some of that information. And so just as some conclusions and takeaways, astrobiology is a cross-cutting science that could benefit from investigations enabled by UOP architectures. UOP could provide important measurements to better understand the habitability of this moon system. And we could discover many surprises about Uranus. We're not really going to know what we get until we get there. And so I really think that it is important for astrobiologists and planetary scientists to keep an open mind about this research. And so again, I want to acknowledge my co-author Erin, who recently published a paper on Miranda, and it's been really wonderful working with her on this publication. And with that, I would be happy to take any questions or hear any thoughts. Thank you very much again for the invitation and for your very kind attention. I hope I've left a significant time for discussion.
Yeah, definitely. Awesome. Thanks so much, Jessica. That was an incredible presentation. I know there's like a clapping. I always forget how to do this, but like I know there's a way to like do the clapping icon. Oh, here it is. Here it is. Right? Did that work? I think so. Yeah, I see people doing it. Okay, great. Yeah, incredible talk. Really, really great stuff. Does anyone have any questions? You can feel free to use the raise hand function, which I think is also down there in the React part of Zoom, or you can, oh, I see. Or you can post stuff in the chat. I'll go ahead and let Tim start. Go for it, Tim.
Yeah, I was only able to pay 75% attention, so maybe you already answered my question. But I mean, for remote observations, something we could really use would be waste gases that would be propellants for plumes, things like that, because that would be far easier to detect than any kind of small outcropping of solid material on a distant planet. So what can you give us about waste gases?
Well, I guess my take would be twofold. Is there's a lot of people who are very capable of replicating very cold conditions and could detect what is coming off experimentally. And then again, I like a mass spec. I think if flying through something and directly detecting it is kind of the in my mind really a
Well,
really
I mean,
standard,
the precursor to the arrival 20 years from now. What can we do over the next 20 years to help prepare for when we fly a mass spec through?
Yeah, I think that I know there are people who are modeling or looking into like transport of these materials on the surface. And I think it would be really interesting to get some of those people talking to experimentalists and seeing what we can actually, test and detect in lab. Certainly they make mass spec instruments that we can hook up to different setups and kind of see what comes off and see how much of it comes off and where it goes and go from there.
All right, very cool. Yeah. Any other questions? Again, you can feel free to post stuff in the chat or use the raise hand function, whatever you're more comfortable with. Let's see. Oh, okay. We've got a question in the chat from Shoshana Cole. So you said that you and Lori Barge co-lead the lab. What's it like co-leading a lab?
I think it's really nice, actually. I think it's good to have let's call it more adults in the room. And then you can split up tasks. So we now have a system where we're, co-mentoring students. And I saw a couple of the summer students logged in, so maybe they could tell you if we did a good job or not. But I think that Lori and I have significant research overlap in our interests, but we have very different backgrounds and let's call it very different pet projects. And so it's really nice that we can come together and kind of use all of our skills to the best of their ability, I think. But again, you'd have to ask the students to see if we're doing a good job.
Awesome. Okay, we got another question in the chat here. This is from Leah Sachs. Can you speculate on the composition of the dark material?
I'm going to leave that to the geologists. There have, there's a number of Cartwright papers where they discuss this. And I think that, my kind of take is I think we should try to make it in lab, which I'm sure maybe doesn't shock you given the talk that I just gave. But yeah, I think that there's people who are much more knowledgeable about that than me. So
Anyone in the audience wants to chime in if anyone has any thoughts, because now I'm kind of curious too what it
I'm
could...
also going to stop sharing so I can see
Okay, sure.
all of you and all the questions. Can't see the chat.
Yeah, but I'm curious if anyone in the audience does have any thoughts on that. If not, maybe it'll be something that we'll find out. All right, hearing nothing. Okay, we got a question here from Brian Palazeski. Have there been any observations of cryovolcanoes on the icy moons of Uranus?
I think that there, based on my reading as someone who is not a geologist or a surface features person, there's possible evidence for cryovolcanism, but I think you should take that up with Aaron, who is probably the expert in my opinion on this.
I would say no, nothing definitive yet. I mean, there's always a lot of speculation, especially when there's limited amounts of data, but definitely nothing definitive.
I did see in one of those really beautiful images of the moons that there was sort of a little bump on one side. I'm sure people know a lot more about that than I do, but that was suspicious looking. I don't know if that is anything. Okay, let's see. All right, we got another question here in the chat from Sophia. Are there any limitations of detection that you suspect, especially with mass spec, in terms of relevant molecules or conditions for prebiotic chemistry?
Yes. Okay. So there are a lot of things to consider for this. So as opposed to a lot of spectroscopy where you're just kind of zapping something, let's say, for this you actually need input of chemicals. And so one input one problem is you've got to find something to fly through that will give you enough of a detection. So as Tim pointed out, we'd maybe have to look for some spot where there is like a plume outgassing, something occurring. So that's point one. And of course, for example, for Cassini, they did get information about the rings. I'm not saying that we should fly this just to look for some potential plume somewhere, but and then point two is you of course need enough of the molecules to actually detect the specific molecule. And there's been work done on this for Enceladus and Enceladus's plume that is like widely published, looking at different molecules of interest, from amino acids to smaller molecules. And I think that for all of this, you have to make some assumptions about what you expect to be there. And so, if you're, for example, looking for high quantities of DNA, I think you're probably gonna have a bad time. Just as an example. But I think that it depends on which molecules you want to detect. And from that, experiments and models can tell you likelihood or not likelihood of presence of materials. But the nice thing is we found at least organic molecules generally to be fairly abundant across the solar system. So I think that is a point in our feather in our cap that it's at least an interesting thing to look for that could possibly be around.
All right, very cool. Okay, I have a question real quick. Okay, so kind of based on the uniqueness of the, you know, Uranian environment and the moons, do you anticipate that there will be chemistry there that we just like don't see anywhere else in the solar system? Or I mean, like what, like are you able to sort of infer like what type of differences in the chemistry you might see there compared to like Enceladus or Europa or Mars or the other objects you study?
Okay, so one thing is if you have so of course temperature plays into this, but ignoring that for a brief second, concentration is something that really matters for reactivity. And so, you know, you can imagine that on these very concentrated, you know, kind of like more muddy ocean worlds where it's not, you know, the large, beautiful oceans that we imagine on Enceladus or Europa, the material at least is more concentrated. And so, you know, you're at least getting your organics, your inorganics to come in contact more often. And so I think that could lead to some interesting reactivity, but this is like a feedback loop. And so it's like, I need to know, you know, so if you say, hey, Jessica, for example, we expect concentration of molecule X to be Y, or, you know, this range, you know, then it's like, okay, we can test that and like kind of say, okay, we've varied the minerals, we've varied the, you know, the pH, and we varied the temperature. And so then from that we can say, okay, well then here's what's most interesting, and then and kind of go down from there. And so I think that you know, my kind of attitude is, I think like chemistry, I view myself and I view chemistry as kind of like a consistent almost, you know, and then each planet is kind of its own little environment. So I think I consider myself to be like a generalist when it comes to planetary, right? You know, my expertise really exists in this chemistry sphere. And so I don't think we're, you know, breaking the laws of physics or something like that, but I do think that there's a chance that we could have really interesting chemistry given possibly more concentrated environments, you know, given different subsets of availability. And, you know, again, there are a lot of moons in the solar system, and we really don't know how they are or how these possible ocean worlds are different. And so especially in one system where we have kind of all of these together, and, you know, there's some like pairing, right? So it's like there's you know, two pairs of similar sized moons, and then kind of Miranda by itself. But, you know, by comparison, we can kind of see like how different these environments could be, which I think would be interesting.
It's really awesome. All right, any other last minute questions, or even just thoughts, comments? You can post things in the chat. You can use the raise hand feature. Anything that folks would like. Kind of pause for a second. In case. Okay, if not, you know, we can stay online if folks have any additional questions. I'll real quick kind of show up the community news slide just because it's tradition now at this point. But I'll just real quick say thank you so much, Jessica. That was an incredible talk, and it really made us all think about what could possibly be there, and I'm excited. I'm stoked for you know, a mission to get out there and really see stuff up close. It's gonna be cool. Okay, all right. I'll go ahead and share the community news slide. So for folks that might be new, every let's see if I can get this. Doing two things at once is hard. Okay, so every Ice Giant Systems seminar series lecture, we kind of throw this slide up at the very end just to kind of get the community involved in things that are going on, you know, happenings, making sure folks know about upcoming meetings that are relevant to this community, but also maybe job opportunities, and you know, maybe even grad student and postdoc positions. So what I'm going to do is I'm going to actually just like grab this and just post it in the chat, and I apologize, but it's like the only way I can get links to you all, because you can't click on the screen. Oh, did that not work? Oh, sorry about the weird image that it also added. I don't know why that happened. Sorry, but everyone sees the text at least, hopefully, right? I didn't even know I could like post an image in the chat. Anyway, all right, so now you have the links. So right, coming up next month is Dr. Richard Cartwright here at APL. He'll be giving a talk September 10th for the Ice Giant Systems seminar series. I also wanted to plug that DPS early registration closes tomorrow. So if you haven't had a chance to get that in, definitely hit that up. Abstract deadline that's also tomorrow is Advancing IDEA conference that's going to be happening in October. And so make sure you get your abstracts in there. I believe registration is also open, and I'm pretty sure it's free. So if you are interested in attending that, I believe it's open and free. I also thought this might be of interest to some folks, so I wanted to include it here anyway. It was only tangentially related, but I thought just in case. So Sky and Telescope, the magazine, has an editor-in-chief position that's open. So if that's something that you're interested in, like science communication and writing, maybe check that out. The deadline is at the end of this month. And then there's an assistant professor position at UC Berkeley in their astronomy department. And you've got a little bit more time for that. The deadline is November 1st for that. And I believe it was sort of an open call. It didn't specify a subfield. I think it was just any astronomy and planetary science professorship. And of course, the OPAG meeting is coming up in November. So there's a save the date. I think registration is open, and it's free, I believe, as well. And I know that there was a change to the date of the OPAG meeting. Like for a while, it was being advertised as early November. So if you have that on your calendar, make sure you get the new date, which is November 20 through 22. And so, and I just saw in the chat. Yes, for those who don't know, IDEA is inclusivity, diversity, equity, and inclusivity, diversity, equity, and accessibility. There we go. So EDIA. And oh, great to hear. 2022 IdeaCon was amazing. Awesome. Thanks, Shoshana. That's really great to hear. Right. So, unless there are any other questions, about anything on the community news slide, or of course, anything for Jessica and her talk, we can kind of close things up a little early and make sure folks have a chance to get to their next meetings. And I can leave the Zoom open for just a minute or two, but hearing nothing, I'll say again, thank you so much, Jessica. Really incredible talk. It's awesome to start thinking about this stuff. And also to hear something a little different, like in planetary science, we often don't hear about astrobiology, but it's important. And so I really enjoyed that. So thanks so much, everyone, for coming. Thanks again, Jessica, and we will see you all next month. Bye, everyone.
Yeah, thank you, Jody, and thank you everyone for coming.